Hi, this presentation is on a framework for the analysis of adaptive systems using Bayesian statistics. This is work done by Johann from the NASA Ames Research Center and Johann Schumann from KBR. When we look at any complex system, like a spacecraft, aircraft, or a complex software system, each of these complex systems can only work safely within a certain region of its state space. Just as an example to explain, this is a chart from the report of the ill-fated Air France AF447 flight, which crashed over the Atlantic. It shows over two parameters here. On the vertical axis, the altitude in feet, and on the right axis, the speed in Mach. When there's a number of boundaries in there separating safe regions from unsafe regions. Safe region is if the aircraft is fast enough at certain altitudes that it can stay safely in the air and fly as normal, then the state is considered to be safe. If the aircraft is getting too slow, then the aircraft is stalling and pretty much very quickly descending or crashing. Here on this chart you can see the red line. Initially, phase 1, the flight is the aircraft is in a safe state, but after the failure of sensors, problems with the board computer, and pilot errors, the point of operation of the aircraft actually crosses these boundaries and go into an unsafe area where ultimately the aircraft stalls and crashes. So you see here, you have this kind of, here just two-dimensional projection, safe regions, boundaries between safe and unsafe regions, which for a safe operation must not be crossed. So safety boundaries, as we saw in the figure, can be nonlinear, so it's not just simple linear or hyper plane in a high-dimensional space. They can be in a very high-dimensional space. The example we show had only two parameters, but you can imagine if there's multiple more parameters affecting the aircraft of the behavior of the system, then we need to analyze a high-dimensional space, and they can be hard to estimate because they include here in this case both kind of physics, laws of dynamics models, as well as potential software. Yet these safety boundaries are very important for a number of reasons, and knowledge about the locations and shapes of the safety boundaries is important for system design, which means the designer needs to know is the current configuration of the aircraft, in this example, is it flying safely in the intended areas of altitude and speed. The knowledge about boundaries is also very important for verification and validation, both on system level as well as on software level, and finally also for system operations. Because it's important to be able to find these boundaries in high-dimensional spaces. We developed an analysis framework It uses a hierarchical Bayesian statistical modeling with active learning in computer experiment design. So when you look at a high-level architecture of our framework here, the overall idea is we have this system under test. In this case, it could be an aircraft, it could be a piece of software, it could be a cyber-physical system, simulation, or other. And we generate a test case, define region, where the system under test does not meet system requirements. So, system requirements, for example, for safety or for performance or for other criteria, are checked with respect to the execution of a test case, and deviations are reported to our framework. And our framework here uses active learning and computer experimental design to incrementally come up with a statistical model and iteratively improving the statistical model to find and characterize these boundaries. Finally, we can perform a geometric shape estimation of the boundaries in order to provide feedback to the designer. Why are we using active learning? Active learning selects new test cases that are close to the estimated boundaries for higher efficiency. That way we can determine boundaries with a lower number of test cases. One specific feature of our framework is we can consider the system under test as a black box. This means we can perform analyses on small software systems, on large simulation systems, without having to internally modify or even have access to the system. However, that said, we also, if information is important about internals of the system, we could model and perform analysis on internal parameters of the system as well. Now let's look at the estimation, how active learning is estimating the boundaries. And we developed a boundary-aware metric for this one. The idea of this metric is at each iteration, given the current statistical model, which means a number of test cases have already been executed, some of them resulted in this point is safe, this point is unsafe, so it's shown in the lower right hand. And this boundary-aware metric proposes new test cases that are close to the suspected boundary, because we want to characterize the boundary, so we want to have as many test cases close to the boundary, and not just in one point above the boundary, but along all the boundary. And also we have to have away from the boundary some test cases, because there might be yet another boundary. So we are also looking in high variance areas away from the boundary. And these three terms of this rather complicated boundary-aware metric correspond to these three criteria. So we execute an iterative improvement of the model, generate new test cases using our geometric boundary-aware metric, until we reach a number of data points. The raw result out of this framework would be a point cloud, as shown here on the left-hand side. Green points correspond to test cases in regions where the system requirement has been fulfilled. The blue ones correspond to violation or unsafe areas. However, just a high-dimensional set of coordinates for these data points is usually not very helpful as a feedback to the designer. So now we are aiming to estimate geometric shapes for these boundaries, which makes it possible to clearly communicate these shapes as parameterized geometric shapes like cubes, spheres, cylinders, cones, something like that, parameterized to the designer. Very often the designer already has some kind of idea, like, well, most likely the safe area of this system has the shape of a cylinder. So I'm not interested in the individual points, but I just want to know if the diameter of the cylinder is smaller or larger than a certain threshold. So our geometric shape estimation now is using Bayesian techniques to convert the point cloud of the statistical model into parameterized geometric shapes. So we do a statistical modeling of the shapes and estimate most likely shapes from a given dictionary provided by the domain expert. On the previous slide we saw like boxes, spheres, cylinders or cones. These are in a library, and the Bayesian estimation routine of our framework gives a best likelihood estimation on the shapes and which shapes and how many shapes are available. In order to accomplish this task, we use a number of 3 metrics. One is completeness, which means each point, each test case from the active learning cycle should be close to some shape S. So when we look at the right-hand figure, top figure, obviously the red points correspond to two intersecting lines. However, if the system only detects as a shape the left-hand line, then the shape estimation has a bad completeness. Secondly, minimality criterion. The shapes should be as different as possible. In the middle panel here, the system has detected 3 lines, 3 solid lines, 2 on the left-hand side and 1 on the right-hand side. Okay, now it's complete, but the left-hand side is covered by 2 shapes very close to each other, which violates our minimality criteria. And finally, the summary metrics is the points on each shape should be close to the data points, which means the system should select estimates which are really on the data points. Here in the bottom panel, the estimated line is ways off from the data points, so this would violate the summary. So with that framework, we are now, with a low number of test cases, are able to find and characterize boundaries in high-dimensional spaces. But now everybody will say, how are you dealing with adaptive systems? So this framework can be used for the analysis of adaptive systems, and it allows us to make analysis to address the following questions. One is safe adaptation. In which regions of the state space is the adaptation always safe? Let's assume, as an example in the paper, a long time ago we did analysis on the intelligent flight control system, which was a neuroadaptive flight controller. When we analyzed the adaptation behavior, we found a boundary which has the form of a sphere. Here we just, on the top panel, we just show one quadrant. Inside the quadrant, the adaptation can be done safely, so the aircraft stays after a damage, stays in the air. If the parameters are outside of this sphere, then the adaptation cannot be guaranteed to be successful. Another important question regarding adaptation is the adaptation speed. If the adaptation is happening very slowly, the system might adapt too slow to reach or stay in a safe state. So again, with the aircraft example, the adaptation might only be ended after the aircraft has crash landed. So our framework makes it possible to predict the failure time, again using statistical techniques. And we also are able to perform analysis on how these safety regions are adapting during or are changing during the adaptation. Here on the bottom right panel, it's the same figure we showed in the initial teaser. On the left hand side, in the gray area, this is the safe region before the adaptation. The red dot is the point of operation. But now the system is adapting, which means the safe region changes its shape and its size. However, we are still at the same point of operation. So this analysis can reveal two things. One is the safe region, or the size of the safe region, stays pretty much the same, which is in most cases a good feature. But on the other hand, the point of operation now is much closer to the safety boundary, which might be a concern for safety, something which might be addressed by the designer of the system. To come to the conclusions, our framework is an advanced statistical model with active learning. It can capture complex boundaries in high-dimensional spaces, and it requires a low number of test cases because we use active learning with a specific boundary-aware metric. We use Bayesian shape estimation for a human understandable feedback to the designer, so we can provide understandable feedback. And as I briefly mentioned, the framework supports different analyses of adaptation impact on system safety. This is just the current state. Future work will include the online analysis during the operation of the adaptive system. The framework I showed so far is intended for analysis during design, development, and V&V. But in principle, the framework can also be executed while the system is in operation. Why is this potentially of interest? Because the statistical model is based on particle filters. which are very well suited for representing dynamical models. And the active learning and our metrics helps to reduce the number of necessary new test cases. And if you have to exercise some test cases on an operating system, example an aircraft while it's in the air, then you definitely want to only use as few test cases as possible. So this is our goals for the future work. Thank you very much.